Let me see, there's a comment. What is the mode of the quiz? Mode, subjective. Okay, subjective. So no worry, won't cost you any marks. It will only give you extra marks. Okay, it will only give you extra marks. But try to score. Hopefully you could. Okay, last week, where did we stop? Okay. Okay, last week we have discussed on recursive functions, right? We have talked about recursive functions. Recursive functions is a functions that call itself, right? So in a recursive functions, there will be a function with the same name as it is calling a functions with the same name as the function itself, right? And in a recursive function, that, as I mentioned also, there will always be conditions that will stop the recursive, right? So this is an example of recursive functions. And from recursive functions, analyzing it is slightly more complicated. We can use the recurrence tree, okay, just like over here. And or we can, as usual, count the number of primitive operations performed, and then from there find out the functions, just like the for the loops, right? Just like for the loops. Or alternatively, we can use the we can come up with the recurrence relations or recurrence equations. Okay, for the recurrence equations, we will have normally you have at least two parts. Okay, one part is the most basic basis operations, and then another, for example, this one is t when n is equal to 0, it performs some constant operations, and then if n is not 0 more than 0, then it performs some recursive operations. Right, so we can write a recurrence equations, and from the recurrence equation we can find out the time complexity using the substitution rule, right? So we have go through this, so I won't be going through this example again, okay, but we'll look at other example today. Okay, so later on, for as I mentioned, recursive functions is used, or recurrence is used a lot in divide and conquer later on. So you always see problems with equations like what I shown here. Okay, so you see equations something like this often later on, but from what you have seen last week, right, or just now, so this one is every time it call the recursive functions, n is reduced by 1, right? But you will see many examples where n is reduced by some b, okay, by divide by b, in fact, okay. So for example, if b is 2, then meaning is the input is reduced to half, okay. In subsequent recursive function, okay. So and in the example that we saw just now also, we only calling as we only calling one recursive every time. in fact, it is possible to call more than one, okay? Depends on the problem, okay? Depends on the problem. You may want to call one or more than one recursive functions. So you might see forms like this. A recursive function is calling the recursive method a times, okay? A times. So a is an integer number, which is 1 or more than 1. And if you look at the recurrence relations that we have, so in this problem that we have, at the node, every time we perform C constant number of operations, okay, some numbers. Okay, so this part is actually the complexity of the branches, okay, complexity of the branches that invite the operations carry out, okay, the operations carry out at the node, okay, just like this one, at every node it performs some constant number of operations. Okay, we can represent with functions. We could represent using a functions. This part here. Okay, so we may see forms like this later on. Actually, in today class, we will see example with this form. Okay. Now, this is a factorial functions we have here. Okay, factorial functions. Parameter is integer n. So look at this factorial. You know how we perform factorial, right? For example, 3 factorial is equals to 3 times 2, right? Times 1, right? This factorial. Okay, so this one way we could write factorial. Obviously, you could use a loop also to write a factorial function. Okay, look at this example that we have here. This is if you look at the name of the functions, they are the same. It is calling it the function itself, but the input, the arguments reduced -1, right? N -1. So n is reduced -1 every time, right? So when n is equals to 0, then it will stop. So this example is similar to these functions that we have, right? This one also n reduced by 1 every time it performs some constant operations. And if you count, okay, how many constant operations perform? 1, 2, right? 3, 4, 5, 6, okay, around that number, right? So what happened is if given n, so it will minus every time, and at every node it performs some constant, in this case 6, right? 6 operations. So it will do n will reduce by 1 every time until n is equals to 0, then the recursive stop and then it return, right? So okay, so this is the idea, right? This is the idea. So if you draw the recurrence tree, you get something like this, okay? Something like this. At every level, we perform some C operations, So it's not difficult to know that the height is n, right? So this is the time complexity. And if you want to come up with the use the recurrence equations to find the time complexity, you get the same answer, right? So if you so the recurrence so the equations end up will be like what we have here, right? Okay, so I believe this you don't have any questions. This should be straightforward. Like how we derive, for example, the recurrence equations using the substitution rule is exactly the same. Okay, so let's look at another example or another problem or another algorithm. Okay, so now we have a binary search. Okay, binary search we have you already know how it works, right? So you have an array, right? Still remember we have an array, then 1 2 3 4 5 6. Okay, we have an array, right? So you have a value you want to search, then you always search the value in the middle, right? So if the value is the same as the value in the middle, then we found what we are looking for, and we return the position of it, right? If it's not the value, if the value in the middle is not the value we are looking for, then we check whether the value is less than the value in the middle or greater than it. If it's less than the value in the middle, we search the lower half, right? If it's more than the value in the middle, then we search the upper half, right? So this is roughly the idea of a binary search. So this process repeats, right, until either we found the value that we are looking for, then we return, or else you will continue searching until we get the value, or the value is not in the list, right? In the array or list. Okay, so okay, let us look at this algorithm. Let us look at the code. So last time I didn't show you the code, right? So this is the code for binary search. Hope you can see it. It's a bit small. Okay, so okay, so okay. So as we have known just from the explanation just now, right? So this part is key not found, meaning is not, if this condition is true, meaning the key is not in the array. Okay, it's not in the array. Okay, if this condition is not true, then we'll continue doing the else part, right? So look at this else part. So midpoint, okay, I didn't put the midpoint function here, okay, due to space, but midpoint basically like what the command here said, calculate the midpoint to cut set in half, right? So in general, to find this midpoint, we just need to know the left positions and the rightmost position, add them out and then divide by 2 roughly, right? So if you look at how we calculate this midpoint, we are doing constant, we are using constant number of operations. Okay, we are doing some constant number of operations. So this is some constant number of primitive operations performed by this midpoint. Okay. Okay, so now here we have this if is we perform a comparison. If you want, you can also count this accessing the item in the array. Okay. So if this is true, then we'll call the binary search recursively again. Okay. If okay, if this is not true, then we'll test these conditions, right? If this condition is true, then we'll be calling the recursive functions again. If both of these two conditions are false, then else will be true, right? This statement will be this condition will be you'll be going into the conditional block, and then meaning we found the items we are looking for, and then it's stopped. Okay, so obviously this is not what if we want to find out the worst case time complexity. Obviously, by looking at this, we know that the time complexity is constant for best case, right? For best case, because if you count, this is just constant number of operations, and then you reach IMID, and then you return, and then the function terminate, right? So that is the best case, but we are interested to find out the worst case, right? To find out the worst case. So either one of these is true, right? If either one of these is true, meaning for every time we are calling, we'll perform some C operations, right? C some constant number of operations, right? And every time we will divide the n by by half. Okay, every time we divide the n by half. Okay, so every time so this is the recurrence relations. So and so this is recurrence equations. When n is equals to 1, okay, we'll return a constant. If n is not 1, n is more than 0, then every time we'll divide n by 2, and then perform some constant number of operations. Okay, perform some constant number of operations at every node, right? So from this recurrence tree, we can see that, okay, we start with n, and then subsequently n divided by 2, n divided by 4, and then continue until n there's only one item, right? You divide n every time, and at the end you only your sub list or sub array only has one item, right? So when it has only one item, you either found the items you are looking for, or the items you are looking for is not in the list or array. Then obviously you will terminate. So we saw this sequence before, right? So if every time n is divided by 2, reduced by half every time. So eventually there's only one item, it is stopped, and then we know that the height of it is log n, okay, log n plus 1. The height is log n, the number of level is log n plus 1, okay, to be more precise. Okay, so we know from this is the time complexity of this is worst case is big O log n, okay, big O of log n. Okay, we could also use recurrence relations to find out the time complexity. Okay, so Tn equals to Tn divided by 2 plus C. So at every node, right? At every node here, we perform some C operations. C, right? C operations. So we perform C sorry. So plus C. So we after that, subsequently, from n divided by 2, then it will divide again, become n divided by 4 plus some C operations. Then reduce by half again, and become n divided by 8 plus C, right? So this continue until T1 equals to that's C, right? So by using the substitution rule, we so we start from Tn equals to Tn divided by 2 plus C, and we know Tn divided by 2 is this, right? So we put it in, substitute it in, right? And then we can simplify these equations as this, right? So 4 become 2 raised to the power of 2 plus 2c. Then and then we do substitution again. Tn divided by 4, we know this is Tn divided by 4. Substitute it in, right? Then we'll end up with this, right? So we can simplify it like this. Okay, then we assume 2 raised to the power of k is equals to n. Okay, so that this part here, okay, so that this part here is equals to 1. Okay, we want to make it 1, right? We want to make this part become 1. Two sorry, 2 raised to the power of k equals to n, so this part become n. Sorry, is it n? Sorry, 2 n equals to 2 raised to the power of k, so this become 1, right? This is correct, become 1. Okay, T1, so we can say T1, this is T1 plus C log n. So T1 you know is constant, so this becomes C log n. So we have to find out what is k, right? 2k equals to n, right? So we put log in front and we put log in front. We bring k down, so k equals to log n, right? So we replace k with log n. That's why that's how we get this. So the time complexity, this is base 2, right? This is base 2. So for time complexity, we don't look at the base. The base is not important because we can always change the base by multiplying a constant. So the time complexity is log n. Right. So we can use either recurrence relations or use this recurrence tree to find out the time complexity to see, you can see which one suit you best. Obviously, this take up more steps. If you draw this, maybe it's clearer visually. Okay, another different functions. Computing power. We also discussed this function before, right? Okay, so this is power. This is also power. So this is recursive, and it's reduced by 1 every time, right? So this is just similar like what we saw earlier, the recurrence equations, or if you draw the recurrence tree, it will be similar, right? Okay. And if you count the number of operations carried out, this is also C constant, and then constant, okay, constant. So at every level, constant number of operations carried out for the when we call the power function recursively. So it's not difficult to see to see that the time complexity is big O n, worst case, okay, worst case. Okay, another way of doing this computing power is using this approach, using these equations here, recurrence equations. N equals to 0 is 1, right? So if you look at the n every time, divide by 2, okay? N divide by 2 every time. Okay, you can from these equations, you have to come up with the recurrence equation actually. So this part is the basis part. Obviously, this is a constant, right? T0 equals to C, right? Then Tn equals to then T. You can do it yourself, I think. The n, if you let us look at what happens. So this k here is actually n, okay? So sometimes if they didn't use n, so don't say there's no n, okay? Sometimes you have to find out yourself which one is the n, okay? This x is just a constant. If you look at constant in the equations, right? Like x. So what happens is this x raised to the power of k. K can be any value. X is just a constant. Okay. So there are two parameters in these functions, right? So in this case is actually n that normally we use. Okay, it's the n that we normally use. And if you look at the value is half every time, right? Okay, so I can draw the recurrence tree, right, as usual, and divide by 2 every time. And we saw this sequence before, right? If we divide n by 2 every time, the height of the tree is log n, right? Okay, so can try out on your own later if you want. It's similar to the binary search that we saw earlier. Okay, now we come to one more complicated example or problems that we have here. Okay, sorry. We come to one slightly more complicated problems. Okay, so this is functions that will draw a ruler. Okay, draw a ruler. Okay. So given some parameter, the function will draw ruler like this. Okay, basically draw the points, right? Okay, or dot, not point, draw the dash, okay, draw the dash. So we want to find out the time complexity for these functions that draw the dash. Okay, so the function is called draw ruler. Draw ruler itself is not a recursive function, but this draw interval is a recursive function. Look at this draw interval. Draw interval, it called draw interval 2 times, right? Okay, so this is an example of recursive functions that is calling calling recursive functions 2 times, right? So draw interval called draw interval 2 times. The earlier recursive functions that we saw, it only call the function once, okay, once every time. So this one call recursively call draw interval 2 times, and every time the n in the central length in this case is n, okay, central length in this case is n, and then n reduced by 1, right? N reduced by 1 until obviously is 0, then nothing is performed, right? N central length will reduce by 1 every time until the central length equals to 0 is stop, okay, stop. It does not call recursive functions anymore, right? You see there's no else here. Okay, draw line. Let's look at what draw line do. Okay, draw line. So there are 2 draw line. Okay, so this is Java codes. Okay, this is called method overloading. This method name, they have the same name, but the parameters are different. One have 2 parameter, one has only 1. Okay, this one calls draw line with a single argument, right? Draw line with single argument. So it will call this one, but this one will be calling draw line with the 2 parameters. This one, right? Let us look at what. So the main draw line. Let us look at what draw line do. Okay, what draw line do. What is the time complexity of this part? What is the time complexity for this part? Yeah, thanks, Sapti. This part, thanks, Raji. So this part is perform n, right? This part perform n operations, okay? This part perform n operations. So you can say it's big O of n, right? So it performs n operations and then perform some constant operations, right? So n plus some constant operations, right? It is constant. So what draw line do is some n plus c, right? Some n plus some constant, right? And we are calling 2 times draw line, right? We are calling 2 times draw line. So the recurrence equations will be something like this, right? 2 e n minus 1, right? Plus n plus c, right? Okay, so this will, as I mentioned, we'll do it until n is equals to 0, right? N equals to 0, then we perform some constant operations, right? So this n is if n more than 0, right, we do this part. If n equals to 0, we do this part, right? Okay, so this will be our recurrence equation. Okay, so let us look at this is visually what visually let you visualize what is being done. So draw line 1, then you draw one dash. Draw line 2, it will draw 2 dash and then 1 dash at the side of it, right? So it will be something like this, right? Here, okay, here to make things simpler, I just count the dash, okay? I'm just counting the dash to make it simple, okay? So if t is 1, then we draw 1 dash, then stop. If t is if n is 2, when we do 2 dash and then 1 dash at the side, okay? So if n is equals to 3, then we will have something like this, okay? If n is equals to 3, we have something like this. So there will be a 3 dash in the middle, and then 2 dash at the side, and then 1 dash at the side of the 2, right? So we will get something like this. So the green one is actually the recursive. You can imagine it as a recursive function, okay? It's the recursive functions, and the blue circle is the draw line, okay? Draw line that. So the number tell us how many times it draw, right? It draw or it print out. Okay. So we have written the recurrence equation just now, right? N equals to 0. Actually n equals to 0. It doesn't perform anything. It is also a constant, right? If you didn't do anything, then it's also a constant. Or it performs something, it's also a constant number of operations, then it's also a constant. Okay, so if n more than 0, then we will call the recursive function 2 times, as I mentioned, and n will reduce by 1 every time plus n. And by the way, should be plus some c. Okay, but here to reduce the number of to reduce the complexity of the calculations, I just show you the higher order n. I leave out the constant. N, what is n? Okay. If n is the maximum number, you can see as a maximum number of dash you want to draw. Okay, you can consider it like this. Okay, you can consider as a maximum number of dash you want to draw. Okay. Okay, so this is our equations that we have. Then when Tn equals to 1, what happens is we will have 2Tn minus 2 plus then n minus 1. Okay, why if you look at this, why here is n minus 1? If you look at here, right? If you look at the when we reduce by 1, right? Let's say initially central length is 10, right? 10 minus 1 become 9 already, right? Then we recursively call draw interval now with 9, right? How many times draw line draw? 9 times, right? then draw interval, call draw interval again, 9 minus 1, right? 9 minus 1. Okay, 9 minus 1 is 8. And then 8, how many times? Draw 8 times. So n will reduce. Based on this, it will reduce, right? When n is equals to 2, it only draw n minus 2 times. When n is equals to n minus 3, it only drew n minus 3 times, right? Clear? So this that is why we have this. Okay, this part is like this. Okay, then we use the substitution rule, right? So we start with this and then replace Tn minus 1. What is Tn minus 1? Tn minus 1 is this, right? So we replace it inside. And then what is Tn minus 1? Then what is Tn minus 2? Tn minus 2 is this. Then you substitute it in, right? So we can simplify it as 2. You see how many 2? 2, 1. First time is second time is we have 2, 2. Third time we have 3, 2. And then also look at the n. So we can simplify it to these equations here. And then we find out assume k is equals to n, then you get this. Okay, we'll get this. And from this, we only look at the higher order n, right? When we look at the time complexity, we look at the higher order n. But okay, so the time complexity, worst case time complexity is this. So this is slightly more complex. Okay, it's more complex. Okay, let's look at one more example. Okay, let's look at one more example before we break. The last example. Okay, the last example is a merge sort. So merge sort is a sorting algorithm. Okay, it is a sorting algorithm that sort an unordered array to become a unordered array become an ordered array, right? Either is in decreasing order or ascending order or decreasing order is possible. Okay. I'm not sure whether you are familiar with merge sort, but let me show you how merge sort works. Okay, how merge sort works. Okay, so let me show you the simulations of it, how merge sort sorts the numbers. So we start with an array with this value 7562813 right? Okay, so every time it will merge sort will split the number to 2, okay, of equal size, more or less equal size. Okay, more or less equals. If it's an odd number, it's impossible to be equal, right? So that's why I said more or less equals have the same length, more or less. Okay, so in other words, what happened is the list reduced by half. The size of the list reduced by half every time, right? So this it just divide and then divide until there is only the array only have the sub array only have one items. Okay, from 8 items become 4, become 2, and until 1, then we cannot split the subarray again because there's only one item. So this is called the white part, the division part. And then the next part is to join them, right? Okay. Okay, let us look at how the merge sort works first before we look at the algorithms, or before look at the pseudocodes. Okay, so now we have only one item in the subarray. So we will compare them. Okay, 5 compared to 7, they are in the right. So we want to assume we are doing sorting them in ascending order. So from small to large. Okay. So 5 compared to 7. So this is the position. They'll be put in this position. 6 compared to 2, we change the position. Smaller value at the left, higher value at the right. 8 compared to 1. So 1 is in front, 8 behind. 3 compared to 4. So 3 in front, 4 behind. Right. Okay. Now we have we have sublist with 2 items. So just like what we did earlier, right? We will compare this. Okay. So we'll put them in. So when what you see here, right? When we join the sub array together. When we join them, the sub array become an order array. Okay, it become an order array. So 5, 7, 2, 6 become 2, 5, 6, 7. 1, 8, 3, 4 become 1, 3, 4, 8. So this merge, calling the merge functions, and then merge again. So now we have a complete order array which is ordered. Okay. Okay. Now let us look at how we did the comparison. Okay. How we did the comparison. How we did the comparison. So let's say, okay, let's say we have these 2 sublists, 2, 5, 6, 7, and 1, 3, 4, 8. These 2, sorry, subarray. So what happened? How the code works? We compare the leftmost item first. 2 compared to 1. 1 is smaller. We put it here, right? Now then we put 2 back. 2 compare with 3. 2 is smaller. We put 2. We join 1 with 2. Okay. We put 3 back. Right. Now we have 5, 6, 7. 5 compared with 3. 3 is smaller. So we join 3 to 2, right? And then we put back 5. Right. So now we compare 5 with 4. 4 is smaller. So we put 4 to 3. We put 5 back. Okay. So you can you know the idea. So I hope you know the idea. So you can complete this on your own. So the purpose of this is to show you how the comparison works. Okay. Later on we will need to count. Okay, we would need to count the operations when we want to find out the time complexity, right? To find out the time complexity, we need to know the details of how the comparison works. Okay, now let us look at the codes. Let us look at the code. So this is the merge sort. Okay, merge sort. Okay. Input sequence S n element comparator, sequence S with n element comparator. Comparator tell us is an normally is an object, okay, that help us to do comparison. tell us how to do comparison. Okay, look at the code. So this is s dot size more than 1. So this is comparison. S dot size, this calling this method, this is a constant also. This is constant, so this is some constant number. Okay. So s is a list. Okay. If you still remember, assuming it is a queue, right? Queue data structure. We talked about queue data structure last week, right? To get the size of to access the size of the queue, for example, it takes constant amount of time, right? Do you remember? If you don't remember, you can check back the data structure. So comparison is take one operations, and then this part also takes some constant number of operations, so it's some C. Okay, so partitions. I think I didn't show you the part. I don't have the partition functions here. Yeah, I don't have the partition function here, but basically partitions will split a list to 2. Okay, will split the list to 2. In this case, it will split the list to half. Okay, in this case, it will split the list S to half. Okay, it will split the list S to half. So we end up with two sublists, S1 and S2. Okay, sublist S1 and S2. And now what happened is it called merge sort 2 times, right? It is calling merge sort 2 times. And what happened is one of the sublists each of the sublists go to the recursive functions that it call, right? Okay, so this is a merge. This is not merge sort. So this merge sort, we call merge sort 2 times. And merge sort will return, and then it will when both merge sort return, then we'll execute this functions merge, right? So what's the time complexity of merge? Then you have to find out. Okay, you have to find out what's the time complexity of merge. Okay, so this creating a list. Okay, you can assume it's as constant, and then inside there's a for loop, right? There's a for loop. So this for loop merge part basically is doing this, right? Doing this comparison, and then we join the sublist together, right? Like for example, 5 7 and 2 6 become 2 5 6 7. We join them, compare, and then join them. How to compare? I already show you here how it compares. First item on the list, compare, and then the one smaller one take out, right? So this how we do the comparison. Okay. It'll be easier. Okay, it will be easier if you look at example. You can as usual do the recurrence tree or recurrence equations, or maybe slightly simpler is use some example and then simulate, right? Use some example and then simulate it. So this one I just look at count the number of comparison, because that's the operations that matters, and then there are some other operations carried out which take constant operations. So the constant one I didn't count. I just count the comparison part. Okay, so when we have the sublist 5 and 7, we obviously compare once, right? This one compare with this one compare. So there are 4 best case. Okay, let us look at best case scenario. There are 4 comparison. Okay, Now at this, when we have a sublist with two items each at at the list. Okay, so it is not difficult to know, to show that for best case scenario you can only do 4 comparison. Okay, so idea is you compare this one with this one, we put it here, and then compare again, you put another one, and then the rest then you can join. So you can try out later. And for this one, when you have 4 items on the sublist, it's also not difficult to show that for best case there are 4 comparison. One simple idea, you just compare this one with this one. Is all, let's say all the value here is smaller than the value here. Let's say this one is 12. So what happens is you compare 1, 2, 3, 4 times. The rest you don't have to compare anymore because this is already ordered, right? Let's say we have value like this: 12, 15, 16, and 17. So how many the best? So in this case, we will have the best case scenario where we only do 4 comparison, and then this one is already sort done, right? So this is the best case. So but for worst case, if you do the simulation, you'll notice that the number of comparison increase like this: 4, 6, 7, and so on. So meaning for worst case is the size of the sublist of this minus 1, okay, of the merge, the size of the merge list minus 1. You can no, I forget the what, but you can I forget the formula already. What is it? I think it's 2 times the size of the sublist plus 1, something like that. Okay, something like that. For the worst case scenario, the number of comparison at the node. Okay, the worst case scenario at the number of comparison at the node. So this is what this is through simulations. You look at how the size increase. Okay, how the number of comparison increase when n increase. Okay, or else you can, as usual, come up with the recurrence equations, and then use the substitution rule, and then find out the time complexity. Okay, so this is the recurrence equations, or you can draw the recurrence tree. Okay, you can draw the recurrence tree. So from n, then every time n divided by 2, so we'll have n divided by 2, n divided by 4, until, obviously, until there's only one item, right? Then we cannot divide anymore, then it will merge, right? It will join back. And we already saw earlier in few examples, every time if n divided by 2, the height of the tree will be log n, right? The height of the tree will be log n. So, and you can find out that at every node it performs n operation. Okay, you total them up. You total these 2 nodes out, you perform n operation. Total all the nodes out, you perform n operations. Right. So it is not difficult to show that for worst case, okay, for worst case scenario, so every level perform n operations, right? Every level we perform n operations. The number of level is around log n plus 1. The number of level is actually log n plus 1, right? And we perform n, okay, we perform n operations at every level. So it will be n log n. So the worst case time complexity will be n log n. If you look at the best case scenario, it is still n log n, right? It is still n log n. Why? Because if you look at this is actually, if you look at the size here, this is 8. When it is 8, it performs 4. You can do a few more simulations, and then you notice that for best case, the number of comparison is n divided by 2, right? Then for best case scenario, at every level you perform n divided by 2. So even for best case scenario, if it's n divided by 2, we know that if you have n divided by 2 times log n plus 1, the time complexity will be big O log n, right? So right, so the constant is the constant is removed, right? And the lower order of n will also be removed, right? Okay, so these are some examples. Okay, these are some examples of finding out the time complexities for the recursive functions. Okay, finding out the time complexity for recursive functions. Later on, when we look at later on when we look at the divide and conquer topics, we will look at more examples. Okay, we will look at more examples because divide and conquer they use recursive. Okay, they use recursive. Most of the solution use recursive. Okay, so I think we stop here. Okay, so if you have any question, you can ask now, or we could take a break. Then later come back at 8:15. So as I mentioned just now, later at the quiz actually start at 8:20. Okay, the quiz start at 8:20. So as I mentioned to you just now, open book, but no discussion. Try on your own. So this bonus plus 3. So the bonus mark will be add up to your test. Okay. If you score 1, then your test will plus 1. If you score 2, then your test will be plus 2. If you didn't score anything, then whatever you get for your test, then is the mark for your test. Okay. So come back at 8:20. You can have 1 hour to try out. Okay. Any questions? Okay, Ken. So later remember to come back to do the quiz. After the quiz, then we'll discuss. After the quiz, then we'll discuss the question in the quiz. Okay. Okay. If you have no questions, then we will take a break. Okay. Thank you.